Thanks so much, Dan, for your super relevant research. I think it might interest a lot of folks in the room, so hopefully you stick around so we can discuss it a little bit further during the break. I'd like to invite our next speaker to the stage, Aishwarya Agrawal, who is an assistant professor at University of Montreal, also a Canada CFAR AI chair and a core academic of NELA. And her research interests lie at the intersection of computer vision, deep learning, and NLP, with a focus on developing AIs that can see and talk. Today, she'll dive into her research, talking about advancing multimodal vision, language learning. Go ahead, Aishwarya.
All right, can you check if everything is all right on Zoom? It's good? Right, let me just take a sip of water. All right, hello everyone, good afternoon. So yeah, I am Aishwarya, I'm an assistant professor at University of Montreal and a core member of MELA. So my research is on multimodal learning, specifically at the intersection of computer vision and natural language processing. And today I'm going to talk about two latest submissions to NeurIPS that we did from our lab. So this is my lab, by the way. We call it Multimodal AI Research Lab. And the work that I'm going to be presenting today is done by some of these amazing students. So let me just, for those of you who might not be familiar, let me just give you a brief overview of what kinds of tasks we try to tackle in the space of vision and language. So one very common task is image captioning, which is the task of generating natural language descriptions for images, right? Visual question answering is another very common task that we evaluate our models' performance on, and we train models for these tasks. So here the idea is to, given a question and an image, the task for the model or the AI system that we are trying to build is to answer this question as briefly and as to the point as possible. Image retrieval is another task, which is the image text matching task. So given a caption, like gray-haired man in black and yellow tie, and given a pool of images, the task here is for the machine to compute similarity between each pair of sentence and image and retrieve the one that has the highest similarity. Image generation is another very common task where we are supposed to generate image pixel by pixel from a given natural language description. To what are the kinds of applications of these kinds of vision and language systems? So there are multiple applications. I'm going to highlight a few. So these can be used as an aid for visually impaired users. So for example, this is the example that I'm showing here is an actual example from a data set called VizViz, which is collected by questions from visually impaired people. So VizViz is an app, and visually impaired users can use that app to ask questions about day-to-day objects. So for example, here the person is asking, what kind of wine is this? These vision and language systems are also useful for organizing photos and querying for photos in general, right? So for online shopping, and even just if you just want to search through, let's say, your photo app, like Google Photos, you can type in natural language query, like find me a picture where I was wearing this pink jacket on top of a mountain, right? So it just gives you a lot of flexibility as a user to query your images. And finally, the long-term goal here is to be to make these systems so powerful that we can have grounded virtual assistants. So for example, we have Alexa now, but what if we have grounded Alexa? So Alexa, who I could ask questions such as, hey, did you see where I left my keys, right? So these agents would be situated in the environment around us. All right, so what is the state of the art in terms of how good current vision and language models are, right? So here I'm showing you an example output from a vision and language model called Flamingo, released by DeepMind I think last year, not released, I guess its model is not released, published, the paper is published by DeepMind last year. By the way, there has been more progress on top of this. So this is not state of the art anymore. The field is progressing so fast that almost every week there is a new paper. Okay, so here what I wanted to highlight is the capabilities of this model. It seemed pretty good to me. So the model is given an image, and it first generates a caption saying this is a dog, it's a white fluffy dog. And then in the gray box, you see the questions that are asked to the model by humans. So the question is, what season is this? The model says, it looks like a summer day. Why do you think so? Because the grass is green and the dog is not wearing a sweater. What breed is the dog? It's Samoyed. Is the dog running? No, it's sitting. Can you describe the pose of its back legs? The back legs are bent and the dog is sitting on its haunches. So this looks like a pretty reasonable system, right? It's not only has the understanding of image and the language, but also seems to have some sort of common sense reasoning, such as if it is summer, then dogs don't wear sweaters, right? That's pretty impressive. So that is what we have as of today. But let me just take you through a very brief journey of like how much progress we have made over the past few years. So on this plot, what I'm showing you is how the performance of the state-of-the-art models improved over past 7 or 8 years on this specific data set called visual question answering. So I worked a lot. I helped co-create this data set, and I worked a lot on this during my PhD days. And we used to organize this challenge at a computer vision conference every year, where we would benchmark the performance of the best model, right? So you can just see the sheer amount of progress that has happened over last few years, right? And basically we are at a point where we are now beating human performance on this benchmark of visual question answering. So the Flamingo model, whose output I showed you, achieves 82% performance or 82% accuracy, which is better than human performance. And I think the state of the art as of today is probably this Pali model, which is from Google. And I'm not sure if there are better models after that. Okay, but today what I'm going to talk about is, all right, we have made a lot of progress. This is really impressive. But are there certain outstanding challenges still to be tackled by these vision and language models, right? What are the kinds of things they fail at? What are the kinds of things we need a specific attention towards, right? So I'm going to talk about 2 challenges in particular. There are many more. So the first challenge I'm going to talk about is fine-grained understanding. So let me explain what I mean by that. By the way, it's related to compositional understanding. So I'm going to use these terms interchangeably. Compositional understanding and fine-grained understanding, and you will see why. Okay, so what I mean by compositional or fine-grained understanding is best illustrated by this example from a recent work called Winogrand, where they released this benchmark or a data set consisting of pairs of images and captions, and the task for the model is to do the matching, which caption corresponds to which image, and only one match is correct for each image caption pair. So here you see basically the unique property of this task or data set is the 2 captions, they have the exact same set of words, they just differ in the ordering, right? So some plant surrounding a light bulb versus light bulb surrounding some plants. And the images in this particular case are also quite similar to each other, but that need not be the case, right? The unique property here is the sentences consist of the same set of words, but they mean completely different things. They have different arrangement of the words, right? And what basically they show is they evaluated recent vision and language models, and they show that the models struggle to do the task, which is the task of correctly identifying the right match. Which suggests that these models their understanding is not in depth, right? They're not really understanding the fine-grained details here, which is basically the relationship between object, whether the light bulb is surrounding the plant or the plant is surrounding light bulb. So that is called fine-grained relational understanding. This is another data set recently proposed by people from Stanford, which essentially makes the same point that if you show these 2 captions, the horse is eating the grass versus the grass is eating the horse, and ask the model to identify which is the correct caption given the image, it fails to do that. The performance is, I think for some models, it is close to random performance, chance performance. This is yet another data set which is in the question answering format, which requires the model to do compositional reasoning. For example, are there cups to the left of the tray on top of the table, right? So model needs to understand each piece separately. What is a cup? What is a tray? What is a table? What does it mean to be on left? And so on, right? And basically the verdict of the community at this point is these models are not good at these kinds of compositional reasoning. So people have also taken steps towards improving compositional or fine-grained understanding of these models. And one of the latest papers, what they do is, you might have heard about CLIP model, which uses this contrastive learning paradigm. So what this latest paper does is it basically adds an additional loss function, or not even loss function, it basically adds hard negatives to the fine-tuning of CLIP model, and they show that it improves this kind of fine-grained understanding, right? So let me just explain that a bit. So typical, so like the standard CLIP model and a lot of other vision and language models which are trained using this contrastive learning setup, they have this basic setup where you have a bunch of images and a bunch of captions where each caption corresponds to each image. And then you train the model to maximize the similarity between the correct image caption pairs and minimize the similarity between the incorrect pairs, right? So the diagonal here corresponds to the correct pairs and the off diagonal corresponds to incorrect pairs. And you just apply a contrastive loss to do this kind of similarity maximization. In this work, what they do is they add additional hard negatives. So for example, the original caption was a black cat sitting on a desk. They generate a hard negative caption, a black desk sitting on a cat, right? So it's basically word order permutations, but meaning completely different things. And now, and also they retrieve nearest neighbor images, which is basically the same idea that you retrieve images which are quite similar to the original image, but it's not the original image, it's a different image, right? And now what you do is, in addition to minimizing the similarity with like random captions before, you also minimize the similarity with respect to the hard negative captions, right? So contrast, basically add a contrast in your contrastive loss, add these hard negative pairs as well. So basically now what you're doing is you're trying to encourage the model to differentiate between, to differentiate with respect to hard negatives also, right? And they showed that that leads to improvement in the performance. But that has this kind of technique, although it's like one step in this direction of improving fine-grained understanding, but it's not sufficient. So what I'm going to tell you is this latest NeoRIP submission by two of my students, where we proposed a few new loss functions and we further improved the performance. So here, basically, what we do is we essentially take the same approach of generating hard negative sentences like the previous approach, but we generate hard negatives in a more targeted manner. So basically, we generate hard negatives corresponding to different types of perturbations. So by perturbing the relationship, by perturbing the adjective and noun relationships, and by just random order permutation. So we generate different kinds of hard negatives just to cover this space a bit better. But the main novelty here is we have two new sort of loss functions. The first loss that we have here is what it tries to do is, in a typical contrastive learning setup, even with this hard negative that I talked about before, they do not discriminate between the true text and the hard negative text within the same modality. What they do is basically say that the correct image caption pair should be ranked higher than the incorrect image caption pair. And the incorrect pair can also be with respect to hard negative. But there is no explicit distinction between the text and text, right? The positive text and the negative text. So there is no distinction within the modality itself. All of this contrastive loss is between image and text modality, right? It's across modality, not within modality. So the first loss function that we added here is basically this, what we call intramodal contrastive loss, which is illustrated here. So this is your hard negative caption, and sorry, this is your true caption, and these points here are your hard negative captions, and you're just trying to optimize your model to push away these hard negative captions as much as possible from the true caption, right? So, and that is formulated in this loss function, which is a very simple, again, contrastive loss, but within the same modality. And the second loss function that we have is called rank loss, which is across modality. So basically in standard contrastive loss, we just say that, you know, the true pair should have higher similarity than the incorrect pair. but there is no notion of margin. By what margin should it do better? And here we just adopted this simple margin loss, where we say that the distance between the image and the hard negative should be greater than the distance between image and the true caption by some threshold, right? So this, we are enforcing a minimum distance between the correct pair and the hard negative pair, and that is formulated here. This TH denotes the threshold. And the last bit of loss functions is, how do we decide what this threshold should be? So there we use the idea of adaptive margin or adaptive threshold to induce some sort of curriculum learning. So basically, intuitively, the idea is, as you start training your model, the model is not good, right? So it will not be able to distinguish very well between the true examples and the hard negative examples. But as the training progresses, you would expect the model to get better and better. So it will get better at maintaining that distance, right? So basically, using that notion, what we do is the threshold that I talked about, we set it, we don't hand define it. It's just automatically defined by the difference in the scores between positive pair and the hard negative pair from the previous iteration. So T-1 is the previous iteration. So basically, during the starting of the training, this gap between the similarities of positive and hard negative pair would be low. So the value of the threshold would be low. And as the training progresses, the model will become better. So as the model is becoming better, we are also increasing the difficulty of the task, right? So higher threshold means more difficulty of the task. So that is basically the idea behind having this adaptive margin. And then we combine all these loss functions. And basically the result is we evaluated on a bunch of these different fine-grained understanding benchmarks, and we obtain better performance than the neck clip approach, which I said only have these hard negatives, right? And in terms of the insights, so we also show, by the way, that each loss function is useful. We do ablation studies, so that's like we do all the needful things. So, but another thing I wanted to highlight is the learning dynamics, right? So this plot, what it is showing is, as the time progresses, as you're training the model more and more, how does your threshold change, right? So you're seeing 4 different curves because we have one threshold for each type of hard negative. So for relation hard negative, we have a different threshold. For attribute hard negative, we have a different threshold, and so on. But all of these are adaptive, right? So we're not defining any of these. It's not a hyperparameter. So basically what you see here is this blue curve, which corresponds to the relation hard negative, that grows much faster. The threshold value, the curve is showing the threshold value. The threshold value grows much faster for the relation threshold corresponding to other thresholds. And that is because the relation hard negatives are easier for the model to distinguish compared to other hard negatives. And that is because of the way we generate these hard negatives. The other hard negatives are basically generated by masking a word and filling that word using a language model. So the hard negative is still a very plausible sentence, but in the case of relation, we just randomly swap words. So that could lead to implausible sentences. So it is easy for the model to distinguish what is plausible and what is not, right? So, but basically the model is, the increasing threshold shows the model's increasing ability to get better and better, right? Yeah, so, and on the right, we are showing the loss function. So you have to realize that as the threshold grows, although it denotes that the model is getting better, it also increases the difficulty of the task because the loss function is more difficult to optimize now. So we had to impose an upper bound. By the way, on this slide, I forgot to mention, there is an upper bound that we have because we cannot let the threshold grow infinitely. So the upper bound is a hyperparameter. And basically, by maintaining this balance, we see that the loss is stabilized. Okay, so I won't go into the details of this because I want to talk about another project. And here we show some qualitative examples, but I don't have time to go into that. Okay, so the other challenge that I wanted to talk about was the challenge of designing effective prompts for zero-shot evaluation. And in this case, we are particularly targeting the task of visual question answering. So I'm sure you must be familiar with the idea of prompting a model. So it originated from GPT-3 paper where basically they showed that you can you take this pre-trained model, and without any fine tuning, you can prompt the model to do different tasks. So here what they're showing is, if you want to teach translation to the model, you can either directly ask the model to translate from English to French, or you could give some examples and the model will sort of learn on the fly, although there is no learning, right? It's just basically adapting to do the task. And there has been a lot of work in NLP exploring what kind of prompts are useful, what kind of prompts are not, and so on, right? But this investigation of prompting techniques has been done much less in the vision and language space. So here in this project that we also submitted to NeurIPS, what we are trying to figure out is investigating what kind of prompting techniques are useful for visual question answering. So here, for example, the task here is question answering. So we take a pre-trained model and the model has not seen VQA examples, right? So we are teaching the task of VQA at test time. So you could directly ask the question, or you could phrase the question in a bit differently and try to see if the model performance improves, right? So, so we investigated this model called BLIP2, which is close to a state-of-the-art vision and language model capable of zero-shot generalization, right? And here, basically, we asked 4 different questions. We explored different ways of phrasing the question, like how much is the model sensitive to different phrasings of the question, or in other words, how much of a performance boost can you get by just phrasing the question differently. We also asked, like, if you add some few short examples, does the performance improve? What if you add image captions as additional visual cues before you ask the question? Does the performance help? And chain of thought reasoning has also been widely explored in NLP, where you ask the model to generate a rationale in addition to generating the answer. So we were interested in exploring if that helps here as well. And we tried a bunch of these different data sets that I don't have time to go into right now. So basically, I'm just going to show you results for each of these different questions we asked. So the first question we asked was, does the choice of question template matter, right? So here, I'm showing you a few different examples. So these are different ways of phrasing the question. So you can ask the question directly, or you can say that your task is, to answer knowledge-based questions. So we have different data sets where each data set has a different flavor. So you can instruct the model about the particular task you're interested in and see if the performance improves. So basically, what we saw here is the models are indeed sensitive to the type of phrasing of the question or the type of instruction you give to the model, and certain models are more sensitive than the others. The other thing is about a few short examples. And here, basically, we feed a few short examples, and these examples are QA examples only. So we don't feed images, right? So we just give question, answer for like some number of examples, and we see if that helps the model improve the performance. And we saw that it does help, although the results are a bit mixed. The most interesting thing that I want to highlight is this setting where basically, before you ask the model to answer the question, you ask the same model to generate a caption first, right? So step 1, give the image, ask the model to generate a caption for the image. And you can use different ways of prompting the model to generate the caption. And then step 2, you take the generated caption, you feed it along with the question to the model. And surprisingly, that improves the performance by a significant amount, right? So it's just a very simple trick that before asking the model to answer the question, you ask the model to generate a caption and then feed the caption along with the question. And basically, and the last thing we tried was this idea of rationale generation, chain of thought prompting, where we are saying, where we are asking the model to also generate the rationale along with generating the answer. And basically, we saw that that does not improve the performance in this vision and language setting, whereas in NLP, they've shown that it does lead to improvement in the performance. So anyways, I think I'm close to the end of time, so I'll just highlight the conclusion here. So in the first work, we basically showed that generating hard negatives and using specifically designed loss functions can improve fine-grained understanding. And this idea of having adaptive threshold is quite a nice idea, because you don't need to do, have different hyperparameters for different thresholds. and this also induces curriculum learning. And in the second work, we basically showed that the different kinds of text prompts can lead to different performance, and you can improve the performance of your zero-shot visual question answering by just designing your prompts better. And incorporating a few short examples, but more importantly, this idea of adding captions generated by the model significantly improves the performance. And yeah, that's it. So thanks, and happy to take questions.
Questions, anybody? Last call.
It's afternoon.
Well, maybe you can ask us what are your questions over coffee as we're going to move on to break, but this was particularly relevant considering that we touched on prompt engineering this morning, and it's nice to see how you're applying it to the language vision space. So a huge thanks again, and I'll let you guys go on a 20-minute break and come back to us.
Thank you, everyone.
The last portion of the talk. Thank you so much.